Imagine this. A suspect hands over a password, unlocking a digital vault right under court order, only for investigators to realize the real evidence is hidden inside an invisible, mathematically undetectable inner safe. Think about that for a second. The suspect complied, the vault is open, but the truth? It's still completely hidden. This is the absolute frontier of digital obfuscation, a space where finding the evidence is really only half the battle. Let's dive right into this explainer.
Welcome to reWant Courseware. Today's explainer unpacks the latest lectures and cutting-edge ideas of Professor Adam Scott Wandt,
who teaches at the renowned John Jay College of Criminal Justice over in New York City. We're pulling directly from his module on obfuscation to show you exactly how modern fraudsters operate and, more importantly, how forensic examiners actually catch them.
Section 1. The Forensics of Obfuscation.
We're taking you on an investigative journey today to really peel back the layers of how digital evidence is intentionally hidden. You see, a sophisticated fraudster doesn't just hit delete and cross their fingers. No way. They disguise files, they embed them, they mathematically lock them up. To understand how we fight this, we have to define concepts like LSB steganography. Steganography literally comes from the Greek for covered writing. A standard image uses values from 0 to 255 for its red, green, and blue pixels, right? Well, LSB, or least significant bit insertion, takes the lowest order bit, which is a change of at most 1 in 255, and replaces it with the suspect's hidden data. Because this tiny shift is completely below the threshold of human visual perception, entire financial spreadsheets or illicit chat logs can be hiding right inside the microscopic, invisible color variations of a totally normal-looking vacation photo. So, here's the million-dollar question. How do you find something you literally cannot see? To fight back against these wild concealment techniques, professional examiners don't just guess. They utilize a rigorous, structured, three-step detection sequence. It's a precise methodology used to reveal what a file truly is. Let's move to the first step of the sequence and see how it all builds.
Section 2. Unmasking spoofed files.
The very first layer we've got to peel back is simple file extension spoofing. Think of this as Obfuscation 101. A suspect knows investigators are going to use basic keyword searches and file type filters. So they just rename a highly sensitive financial ledger, let's say q3ledger.xlsx, to look like a harmless image file, like vacation.jpg. To a casual observer or a basic operating system search, it's just a picture. But examiners defeat this trick by extracting what we call magic numbers. These are hexadecimal byte sequences at the very beginning of a file's internal header. Take 54B0304, for example. That specifically identifies a zip archive, which happens to be the underlying structure of modern Office documents like Excel files. So if an automated tool sees a file named JPG, but that internal header reads 54B0304, the examiner instantly knows the extension is spoofed. It proves the true structural format, totally regardless of what the file is named.
Section 3. Hidden Data and Steganography.
But what if the format isn't spoofed? What if the suspect actually used LSB steganography, like we talked about earlier, embedding their illicit records directly inside legitimate image data? The file genuinely is a JPEG, but it's carrying a secret payload. Faced with a massive corpus of images, say a seized hard drive with 10,000 photos, an examiner obviously can't check them all manually. They have to rely on statistical Steganolysis tools to triage. They're looking for files that are anomalously large for their visual resolution, or maybe they have conflicting metadata timestamps. Most importantly, tools like StegDetect analyze the mathematical anomalies in pixel distributions. An unmodified natural image has very predictable pixel patterns, but an image stuffed with hidden data, that shows statistical anomalies that the human eye cannot perceive, but the algorithm catches immediately.
Section 4. Cracking the encryption barrier.
Okay, so our Steganolysis tools flag an image, and we extract the hidden payload. But wait, there's a problem. Once we uncover that the data isn't just hidden, but mathematically locked inside encrypted containers, we move to the next layer of the investigation. The fraudster knew we might find the file, so they encrypted it. How do we even prove it's encrypted and not just corrupted garbage data? We map the storage volume looking for its Shannon entropy score. Shannon entropy measures data randomness on a scale from 0 to 8. Plain text has low entropy because human language has predictable patterns. Modern encryption, however, deliberately destroys those patterns. So, when an examiner sees a contiguous region of a hard drive with an entropy score approaching 8.0, the scale's absolute maximum, that flags a region of pure randomness. It's a massive, glaring neon sign that an encrypted container is sitting right there. Discovering an encrypted container brings us face-to-face with the lock itself, the password. And folks, the landscape here has radically changed. We are now dealing with the new federal NIST SP 863-4 password standard. This standard fundamentally tosses out those outdated legacy complexity rules. You know, the ones requiring a frustrating mix of uppercase letters, symbols, and numbers like P@SWORD1W. Instead, it heavily favors a much more formidable 15-character minimum length for single-factor authenticators, and it explicitly prohibits predictable composition rules.
So, why does length matter so much to a forensic investigator? Well, investigators aren't sitting at a keyboard manually guessing passwords. They extract hash values and run them through crazy powerful GPU-accelerated tools like Hashcat in a lab. Dictionary attacks use huge lists of breached passwords. Rule-based mutations systematically tweak those words, maybe capitalizing the first letter or adding a year at the end, which perfectly exploits those old legacy complexity rules. But a pure brute force attack, testing every single possible character combination, the shift to a 15-character passphrase makes brute force enumeration exponentially more difficult, essentially defeating it entirely against modern encryption formats.
Section 5. The Legal Battleground.
So what happens when the password is 20 characters long, totally random, and computational brute force completely fails against modern encryption like AES-256? Well, our forensic investigation hits its ultimate mathematical wall, and we have to transition from the laboratory straight into the legal arena. This is where it gets incredibly complex. Law enforcement agents must carefully navigate some pretty severe constitutional constraints. They have to deal with the specific scope of Fourth Amendment search warrants. Like, if you crack a password looking for financial ledgers and find something entirely unrelated, is it even admissible? Then there are the massive complexities of Fifth Amendment protections against self-incrimination. Is forcing a suspect to hand over a password equivalent to forcing them to testify against themselves? And if it's Face ID or a fingerprint instead of a typed password, the legal rulings across jurisdictions are honestly still completely unsettled.
But investigators do have a powerful legal tool up their sleeve: the foregone conclusion doctrine. Courts can legally compel a suspect to decrypt their data, bypassing that Fifth Amendment issue, but only if the examiner has exhaustively documented prior specific knowledge of the container's existence, its control by the suspect, and its contents. Basically, if the examiner's earlier entropy mapping and file analysis heavily proves the evidence is undoubtedly in there, making the password production a foregone conclusion, the judge can actually force the suspect to open it.
But this brings us right back to our opening paradox, highlighting a scenario that literally keeps forensic examiners awake at night. Applications like VeraCrypt allow a suspect to create a hidden inner volume inside the main encrypted container. They require totally separate passwords. And mathematically speaking, a container with an empty inner volume looks absolutely identical to a container with a full inner volume. So picture this: the suspect legally complies, gives the judge the password to the outer volume containing harmless vacation photos, but still successfully hides the true financial data in the inner volume.
This is the ultimate roadblock. This plausible deniability architecture pushes digital privacy to its absolute extreme. The suspect can look a judge right in the eye, hand over a password, and the investigators have absolutely no mathematical way to prove the secondary, hidden evidence even exists. It leaves us to seriously question how on earth lawful forensic investigations can adapt to mathematically undetectable evidence in the years to come.
The tools to hide are evolving just as fast as the tools to detect. As plausible deniability becomes mathematically bulletproof, we really have to ask ourselves, are we entering an era where some digital crimes are simply unsolvable by design? If you found this breakdown of Professor Wandt's lecture fascinating, please like, follow, and subscribe for more deep dives into emerging technology, digital investigations, and the ideas shaping our future. And remember, stay curious and want knowledge.